Chapter 4, Section 4.5, Exponential Growth and Decay, Modeling Data. The objectives in this section include modeling exponential growth and decay, using logistic growth models, choosing an appropriate model for data, and expressing an exponential model in base E. In the problem area, we'll do this last item and we'll convert in both directions. Let's take a look at exponential growth and decay models. There are two basic types. Exponential growth, as illustrated here. This is a typical exponential growth model, and this represents typical exponential decay model. You can see that with the typical exponential growth model, we start at the initial value here of A0. A0 represents the initial quantity here, and that is because when time is equal to 0, e to the 0 is 1, and 1 times A0 is A0. So they have a y-intercept here at A0, that's the initial amount, in other words, when the time is 0, and then they increase very, very rapidly. Exponential decay works the same, except the value in the exponential model k is now negative, and that makes the curve decrease. We still begin at the initial quantity A0, and we decrease as time goes on. The t-axis here represents a horizontal asymptote, which doesn't apply in application problems because that would mean the curve approaches the x-axis for negative values. Usually t here represents time. For exponential decay, then they do come into play because the graph will always stay above the x-axis. Let's take a look at an example. In the year 2000, the population of Africa was 807 million, and by 2011, it had grown to 1,052 million. Use the exponential growth model, A equals A0 e to the kt, in which t will measure the number of years after the year 2000 to find an exponential growth function that models the data. So in order to do that, we need to determine the initial quantity here, A0, and the value of k. We'll begin by measuring time from the year 2000. So when t is equal to 0, this will correspond to the year 2000. The population in that year was 807 million, so the initial value A0 is 807. The second piece of data is that 11 years later, in 2011, this is now the value of the population. So when t is 11 years later, the A is now 1,052. So we substitute 11 for t and 1052 for a, and we solve the exponential equation. First, isolate the exponential by dividing both sides by the initial quantity, and then by taking the logarithm of both sides. On the left, you take the power property, in which case the 11k comes in front, and on the right side then, we have the log of that ratio. And then, solving for k, we end up with approximately 0.024 to 3 decimal places. So always remember that you have to write down what that exponential model is, and here is that statement. Here's the initial amount, the population at time 0, which represents the year 2000, and then k here, 0.024, actually represents the growth of the population. And in fact, it is a percentage. So 0.024 corresponds to a 2.4% growth in the population over the time period in which the model is valid. Let's look at another example. Exponential decay. The half-life of strontium-90 is 28 years. Half-life means that after 28 years, half of the original amount of the substance will be remaining. Independent of how much you start with, no matter what quantity it is, After 28 years, you will have exactly half of that initial amount left. That means half-life. Let's find an exponential decay model for strontium-90. So we start out writing down the exponential model, A equals A0 e to the kt. And notice that we don't have time and we don't have an initial amount. The initial amount we will just designate as A0. So how is it possible to find the exponential model? Well, after 28 years, which is the half-life time, exactly 1/2 of the original amount present will be remaining. Since we have A0 on both sides of the equation, dividing both sides by A0 will make it be eliminated, and that now has only one variable in it, which is k, and we can find k in the same way as in the previous example. So we take the logarithm of both sides, use the power property on the right side, and then divide both sides by 28. So this is the approximate value of k. Notice that it's negative, which means that we have decay here, decreasing exponential function, rather than growth. So we will start out on the y-axis at a high value, which is the original amount A0 of the substance, and over time that amount will decrease like this until eventually there will be nothing left. Now we write down that exponential model, A equals A0 e to the negative 0.0248t, and yes, the negative 0.0248 means that the amount of substance of strontium-90 will be decreasing by 2.48%. Let's take a look at a different type of exponential modeling here called logistic growth models. Logistic growth models are somewhat different. They represent a ratio of two quantities. We have a constant in the top, c, which is greater than 0, and you have an exponential expression in the denominator with e to the negative power. The value of the b is always greater than 0. These exponential growth models, here there's only one, these are growth. Exponential logistic growth has the following type of characteristic. They are S-type shapes, which generally start out an initial quantity right here, and then they increase very rapidly, so it curves upward like that, and after some point, they begin to decrease the rate at which the function rises, and then they begin to level off. So they have a period of rapid rise, followed by a period of much slower growth. And generally, this value here is called a limiting value. It's the value of the function after a significant amount of usually time, and usually that's designated as L, which is the limiting value. There are also exponential logistic decay models, and they come in a variety like this, where they decrease quite rapidly, and at a very special point they begin to decrease less rapidly and trail off like that and level out. And usually you have a limiting value down here. But we're only modeling today the growth logistic models. Let's take a look at an example. Example 3. In a learning theory project, psychologists discovered that this logistic growth model is a model for describing the proportion of correct responses, f of t, after t learning trials. Find the proportion of correct responses prior to learning trials taking place. Okay, so learning trials take place, that means t is greater than 0. 1, 2, 3, 4, 5, 6, etc. trials. This is prior to. So we are going to let t be 0, and substituting 0 in the function, we'll then compute e to the 0, which is 1, add 1 plus 1, and divide by the numerator, and we get 0.4. So since This is the proportion, or the percentage, 40% of correct responses will be registered prior to the learning trials taking place. And we assume if this is an increasing logistic function that over time the proportion, that percentage, will increase. But only to a point, because it will have a limiting value most likely after a sufficient amount of trials. We'll take a look at an example later when we do the problems. Example 4. This table shows the population of various cities in thousands and the average walking speed in feet per second of a person living in the city. So we take the data, population in thousands and the walking speed. Our function will be the walking speed, and the population in thousands will be your variable here. We'll plot that on statistical plot. If you use your graphing calculator, then you can apply this quantity here to be list 1 and this quantity here to be list 2, and then you're going to plot the walking speed as a function of the population. So the model would be something like that. And we get a curve, at least a hint of a curve, that rises and starts to level off. One natural question we can ask is, based on that scatter plot shown, what type of function would be a good choice for modeling the data? And we'll take a look at this over in the problem area. The brief answer is functions that tend to level off like this after a rapid rise are often logarithmic in nature. They could be logistic if they exhibit an S-type shape. If they do not, then generally a logarithmic fit would be best. That's the conclusion of section 4.5.